Hello, everyone. So last time we were looking at expected values or first moments to derive bounds on minimum number of Hamiltonian paths in a tournament. Now today we also want to again look at expected values or first moments, and of course use probabilistic methods to derive bounds, this time on an independence number of a graph. And later we will also look at the basically chromatic number of graphs. Well, the method that we are using today will be still expected values or first moments, but it has one difference with what we did last time. So today we will use expected values to prove a similar structure exists with a positive probability Okay, so far when we use probabilistic method, we saw that in order to prove existence of a structure with a desired property, we can show that such structure exists with positive probability, and then that proves the existence of such structure. But this time we will see that we cannot, in some cases, we cannot prove the existence of the structure that we are looking for exactly, but we can prove existence of a structure with similar property of what we are looking for, and then we will modify that property in that structure in a deterministic way to get the structure that we need. So with a positive probability, and we will modify it, or let me say alter it, to obtain the structure, the desired structure. Such method is called alteration. Okay, because we are going to modify the structure after applying probabilistic method. We're going to modify the structure to get the structure that we need. So this is called alteration. Okay, now let's look at the bound that we need for the independence number of a graph. So finding a lower bound on independence number of graphs. So let's remind ourselves about independence number. The independence number of a graph G, denoted by alpha of G, is the size of largest independent subset of G. Or the largest independent set in G. Okay, so basically what is independent set? Independent set is the opposite of clique. You know, we saw that for a click in a graph means basically a complete graph inside the graph where any two vertices are connected to each other with an edge. But independent set is the opposite. So if you have a independent set in G, that means set of vertices where none of them are connected to each other with an edge. Okay, so the size of largest independent set is called independence number and denoted by alpha of G. Okay, so let's look at an example. Let's say if I have let's do a very simple example. Let's say this example, V1, V2, V3, V4. So this is a graph with 4 vertices and only one edge. So what is alpha of G here? So this is my G. Alpha of G is, well, the size of largest independent set. Well, obviously the whole graph V1, V2, V3, V4 is not an independent set because there is an edge between V1 and V2. So, but if I, so it cannot be 4, the independence number cannot be 4, but I can find basically 3 vertices, V1, V3, V4. So this is an independent set in G because when I can say V1, V3, V4, when I can say any two vertices inside this set, none of them are connected with an edge. Basically, V1 and V3 are not connected, V1 and V4 are not connected, V3 and V4 are not connected either. So there was no independent set of size 4, but there is an independent set of size 3. So alpha of G is equal to 3. Okay, now let's see look at the lower bound for the independence number of a graph. So this is basically the theorem that we're going to prove. Let G be a graph with n vertices and m edges, and assume that D defined as 2m over n is bigger than or equal to 1. Okay, so there is an assumption in this theorem that D, which is 2m over n, is bigger than or equal to 1. Now, what is D? D is the average degree for this graph, right? So average degree, how do you find the average degree? You have to add the degree of all vertices divided by number of vertices, which is n, and the sum of all degrees is going to be 2 times number of edges, right? Because for each edge is going to be counted twice. Each edge has 2 endpoints, so it's going to be counted twice. And the total number of degrees is 2m divided by n is the average number of degrees. This has to be bigger than or equal to 1 if you want to apply this theorem. So let me say note D is the average and degree. Is the average degree for G. Okay, then so if you have a graph G with n vertices and m edges, and if these, which is 2m over n, is bigger than or equal to 1, then alpha of G is bigger than or equal to n squared over 4m, which is same as n over 2d, right? N over 2d, because these are defined to be 2m over n, is obviously same as n squared over 4m. So the lower bound for independence number of any graph G with these conditions is n squared over 4n. Okay, before proving this theorem, and let me give you some remarks. So one is that, let's try to see whether this lower bound makes sense. So let's say if you have a graph, let's say if you fix, for example, number of edges, okay? If you fix number of edges, and let's say you increase number of vertices, what should happen to independence number? Well, in order to have independence number, we need to find independent set, of course, with largest possible size. But so independent set means what? Means a set of vertices when not any two of them that you consider they are not connected, right? So let's say if you have fixed number of edges, let's say 5 edges, as I increase number of vertices, it's easier for me to find an independent set, right? Let's say if you have 5 edges with 7 vertices compared to 5 edges with 50 vertices. Of course, when I have 50 vertices, I can find an independent set easier, meaning that I can find this independent set with larger size, right? So independence number, which is the size of largest independent set, also increases, right? So if we fix m number of edges and we increase n number of vertices, independence number should increase. So which is consistent with this. The lower bound for independence number is proportional to n squared. So as you increase n, lower bound also increases. On the other hand, let's say if you fix number of vertices and you increase number of edges, let's say if you have 10 vertices and 3 edges compared to 10 vertices and 8 edges. Of course, if you have higher number of edges with fixed number of vertices, it's harder for you to find an independent set, a set where not any 12 vertices that you consider, none of them are connected to each other. So if we fix n and as we increase m, we expect the independence number to decrease. So that's why m is appeared in denominator in the lower bound for independence number. Okay, so this is one remark that I want you to notice before we prove the theorem. Another remark is that the condition that we had in this theorem, which was saying that 2d equals 2m over n bigger than equal to 1, cannot be removed. Why cannot be removed? Well, if I can find an example for which this condition is not met and the theorem does not hold, so that means the condition cannot be removed, right? And the example, I actually just gave it a few minutes ago. Okay, this example, this is a graph with 4 vertices, so n is 4 and only 1 edge, and alpha of g is 3. Okay, so let me say here that in example above, n is 4, m is 1, and alpha of g is 3. So here 2m over n is not bigger than equal to 1, and the theorem does not hold either. And alpha of g is not bigger than equal to n squared over 4m. Why? Because n squared over 4m, if n is 4 and m is 1, would be 4, and 3 is not bigger than or equal to 4. Okay, so now let's prove this theorem that we want to find the lower bound for independence number. So proof charge the pencil. So proof. All right. So about the proof, let's look at the theorem again. See, we have a graph G, which is given to us, and we want to prove a result about it. Well, this time is a little bit different than many of the theorems that we have proved before, because if you think about it, in the theorems we proved before, we were trying to prove existence of a graph G with some specific properties. And we considered a random graph, and then we showed that, and there is a graph with desired property with positive probability. But this time, G is fixed and is given. So I cannot consider random graphs because G is given to me. I want to prove a result about it. So if I want to still use the probabilistic method, what can I consider randomly this time? Okay, so I have no control over G. G is fixed, is given to me. If I want to consider something randomly, it's going to be subsets of G. Subsets of basically vertices of G. Okay, so that is what I can consider randomly this time. Okay, so this is, please note about this difference that, G is fixed, G is given. I have no control. I cannot consider random graphs, but I can still consider random subsets of vertices of G. Okay, so we're going to consider a random subset S of subsets of vertices of G. Okay, now vertices of G, we have n vertices by assumption. So let's call them V1 to Vn. Okay, now I want to describe how this random subset S is chosen. Okay, so this is a random subset of vertices of G. So I have to say, like, basically each of these vertices with which probability they are going to appear in S. Okay, so let me say where each vertex Vi is appeared in S independent of other vertices and with probability P. Okay, like most constructions in this course, where we consider, for example, random graphs, when we consider, for example, the edges, we say each edge appears in the random graph, for example, with probability P, and each edge is independent of other edges. Similarly here, we are saying that, but we are considering a subset of V, which is V1 to Vn. Now V1, the first vertex, is going to be appeared in S with probability P. V2 also is going to be appeared with probability P and independent of whether V1 is appeared or no. V3 is again going to be appeared independent of whether V1 and V2 are appeared in S, and each one with probability P. Okay, so this is how S is constructed. Now, let X denote the number of vertices in S, and let Y denote the number of edges appeared in the induced subgraph G of S. So I have a random subset S, okay? There are some vertices in S. Number of vertices, I'm going to call it capital X. So capital X is a random variable. And the outcomes of this random variable could be 0 if no vertex appears in S, or 1 if one vertex appears in S, all the way to n if n vertices are appeared in S. And well, S itself is a subset of vertices of G. It has no edge. But if I consider the induced subgraph of G induced by S, then there could be edges there, right? So remember, what is the induced subgraph? So when I say G of S, what do we mean? So let's say, let me remind you, let's say, for example, if S contains, for example, V1 and V3, for example, and you want to know whether in the induced subgraph G of S, there is an edge between V1 and V3 or not, okay? So you have to look at the original graph. If in the original graph there is an edge between V1 and V3, in the induced subgraph you also include an edge. If no, then no edge between V1 and V3. Okay, so once you fix the vertices, you have to look at the original graph, whether there are vertices, whenever there's vertices between whenever there's edges between two vertices of S, in the induced subgraph, you have to include the same edges. Okay, so Y is going to be number of edges appeared in the induced subgraph. Okay, so again, Y is also a random variable. What are the possible outputs of this random variable? There could be 0 edge in the induced subgraph, 1 edge, or all the way to M edges, because remember, my assumption is that G has M edges in total. So of course, in the induced subgraph G of S, I cannot have more edges than the original graph. So Y can be 0, 1, all the way to M. Okay, now note, so as we said that X and Y are random variables, but what type of random variables are they? See, I'm saying X is the number of vertices in S. Now, see, choosing S is a random experiment consisting of n random trials, n independent random trials. The first random trial is whether the first vertex V1 is appeared in S or not. And it has two possibilities, success and failure. Success means if the vertex is appeared, which happens with probability P. Failure means if the vertex is not appeared in S, which happens with probability 1 minus P. Second trial, whether V2 is appeared, again with probability success P and probability of failure 1 minus P, and all the way to the last vertex Vn. Okay, so these are basically binomial random variables, and similar case for capital Y. So I'm going to explain that. So X is binomial random variable with which parameters? There are n trials, as I said, for choosing n vertices. Each one with probability success P, which is the probability that those vertices appear, and failure 1 minus P for not appearing. And Y is binomial random variable, which parameters? Well, for Y, again, I have M independent trials because I have M edges, so I can call them edge number 1, edge number 2, all the way to edge number M. Now again, edge number 1 can appear in the induced subgraph or no. Again, either success or failure. Success if it appears, failure if it does not appear. Now, what is the probability of success this time? When can I say that the first edge appears in the induced subgraph? If both vertices of the endpoints of the first edge appears in S. So yeah, I will repeat one more time. The first edge of the graph G appears in the induced subgraph if both of the vertices, which are the endpoints of the first edge, appear in S. If they both appear in S, in induced subgraph, the corresponding edge will also appear. So the probability of success, which means probability of appearing the first edge, is same as probability that both vertices corresponding to the first edge appear in S. Each vertex appear in S with probability P. So probability that those two edges, both of them, appear in S is P times P, because remember, choosing vertices are independent of each other. So each one P, both of them will be P times C, which is P squared. So each edge appears in the induced subgraph with probability P squared. How many edges do we have in total? M edges, which is number of trials, and each one with probability of success P squared, which is the probability that those edges appear in the induced subgraph. Okay, so we have two binomial random variable, and hence I can find the expected value of these random variables. Expected value of X is going to be NP, and expected value of Y is going to be MP squared. And this implies that expected value of X minus Y is equal to NP minus MP squared. Expected value of binomial random variable is NP, right? So NP for the first one, NP squared, and X minus Y, well, because X and Y are random variables, X minus Y is also a random variable with this expected value. Okay, now I want to use another fact that we proved and used last time. So recall that probability of X bigger than or equal to E of X is always positive. We saw this before, and proved before. Okay, remember in this course, we are always looking to prove, some specific structures exist, and to do that, we prove that they exist if we choose the graphs or structures, randomly, then they exist with positive probability. So one useful inequality is this inequality because it says probability of something is positive. Probability that a random variable is bigger than or equal to expected value of X is always positive. Similarly, probability of X less than or equal to E of X is also always positive. Now I want to apply this inequality for the random variable X minus Y, okay? So, because as I said, X minus Y is also a random variable. So that means probability at X minus Y is bigger than or equal to expected value X minus Y, which is NP minus MP squared, is bigger than 0. So what does this mean when you say probability of X minus Y bigger than or equal to this number is bigger than 0? That means there exists a subset S of subsets of the vertices of G for which the difference between a number of vertices and number of edges is at least NP minus MP squared. X denoted number of edges, Y denoted number of X denoted number of vertices, Y denoted number of edges in a random subset S. Now, if probability of X minus Y bigger than some number is positive, means there exists at least one S for which the difference between number of vertices and edges is at least NP minus and NP. Okay. Now, what is the connection of this with the original goal? What was the original goal? Finding a lower bound for the independence number. Now, if I want to find independence number, what should I do? I have to find independent sets. Independent set means sets where any two vertices that I consider, none of them are connected with an edge. So how can I obtain such set? So far, I have a set where the difference between number of vertices and edges is some number. Okay, let me explain this to you with an example. Let's say if this expression NP minus NP squared, let's say we don't know what number it is, but let's say if this is, for example, 3. So that means I have a graph, I have a subset where the difference between number of vertices and edges is at least 3. So what can that subset be? It can be a subset with, for example, 7 vertices and 4 edges, right? So let's say, for example, I can have 3, 4, 5, 6, 7, 1, 2, 3. Right? Or I can have, for example, 8 vertices and 5 edges and so on. But how can I obtain an independent set? Because I want to derive bound for independence number. So this is my set right now. If I want to have independent set, that means I have to get a set where it has no edges in it. In other words, I have to get rid of all the 3 edges that I have here. 4 edges, sorry. So 7, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 vertices and 4 edges. I need 4 edges. This is 4 edges and the difference is 3. So I want to get rid of all the 4 edges here to get an independent set. How can I do that? Well, one way to do that is to delete one vertex from each edge. See, if I delete, for example, one vertex from each edge, let's say this one from this edge, this one from this edge, and this one from this edge, and this one from this edge. Okay, so then once I delete 4 vertices, one vertex from each edge, I'll get a set with 3 vertices, which is this one and this one and this one, and this new set contains absolutely no edge in it because I've already ruined all the edges I had before by deleting one vertex of each of them. So in the new subset, I have no edge at all, which means I have an independent set. Okay, so this is basically the idea. So let's try to write this down. So let me call this set S1. Now next, delete one vertex from each edge in G of S. then G of one vertex from each edge in G of S1, basically I call this. Then we get a set S2, right, with at least how many vertices in at least? Well, I'm deleting one vertex corresponding to each edge. Okay, so, and I know that the difference between vertices and edges is at least np minus np squared. So I'm going to get a set S2 with at least np minus np squared edges, such that G of S2 contains no edge, i.e. S2 is an independent set. So think about the example where np minus np squared was 3. So that means, I could have, for example, 7 vertices and 4 edges. If I delete one vertex from each edge, how many vertices have I deleted? 4 of them I have deleted. And I had 7 in total, so I'm left with 3. But let's say if I have, for example, 15 vertices and 12 edges. Again, if I delete one vertex from each edge, that means I have deleted 12 vertices. I have 15 in originally, so 15 minus 12, again, I'm left with 3. So basically, I can also say that to justify this, more formally, note S2, say if S2 has N2 vertices and M2 edges with N2 minus M2 bigger than equal to NP minus NP squared. S2, so if the original S1 has this many vertices and this many edges, S2 has how many vertices? Has N2 minus M2 vertices. So, and N2 minus M2, we just said is at least, because S2 has N2 minus M2 vertices because we are deleting one vertex corresponding to each edge. And I had M2 edges, so S2, the new set, has N2 minus M2 vertices. And I am assuming that N2 minus M2 is at least NP minus NP squared. So that means S2 has at least NP minus NP squared vertices. Okay. Well, NP minus NP squared, by the way, doesn't have to be integer. If it's, for example, 2.5, means S2 must have at least 2.5 vertices, which means it should have at least 3 vertices. Okay. Well, that's it. So we're almost done. What have we shown so far? We use probabilistic method to prove existence of a set S1, where it wasn't exactly what we were looking for. But once I deleted one vertex from each edge inside induced subgraph induced by S1, then I got a new set S2, so we altered S1 to get a new set S2, where it's an independent set with at least this many vertices. So what does this mean? Therefore, alpha of G, the independence number of G, is going to be bigger than or equal to the size of S2. Because independence number is the size of largest independent set. Well, I already got an independent set S2 with NP minus NP squared vertices, but I'm not sure whether this is the largest independent set. So I can say that alpha of G is bigger than or equal to size of S2, and size of S2 we just said is bigger than or equal to NP minus NP squared. Okay, so what is left to do? So it is left to choose P. Okay, so please note that I haven't chosen P yet. So we said in the beginning that we are going considering a random subset S of vertices of G, where each vertex appears independent of others and with probability P. But we haven't chosen P yet. Now, how do we choose P? Well, we know that NP minus NP squared is a lower bound for alpha of G. Of course, we want the lower bound to be as large as possible, right? So it's left to choose P such that that maximizes NP minus NP squared. So this is a simple, middle school or high school problem, depending on how you look at it. So d to dp of np minus np squared, you can also complete this square to find the p that maximizes this. That's why I said it can be also middle school. But anyways, if you differentiate it, you put it equal to 0, then you get n minus 2mp equals 0, and that gives p equals n over 2m. So is this solution for P acceptable, n over 2m? Well, here is where we use the assumption that we said 2m over n is less than or equal to 1. Okay, so and 2m over n is bigger than or equal to 1. So note P is less than or equal to 1 because by assumption 2m over n is bigger than or equal to 1. I cannot accept a probability which is bigger than 1. But this number n over 2m is less than or equal to 1 because my assumption was 2m over n is bigger than or equal to 1. Okay, so that means alpha of g is bigger than or equal to, well, it was np minus np squared. I just established that the p-value that maximizes is lower bound, np minus np squared is n over 2m. So it's going to be n times n over 2m minus mp squared. So m times n over 2m the whole squared. So this is n squared over 2m minus n squared over 4m. And this is n squared over 4m. So that's it. So we proved this lower bound for the independence number of a graph. So using basically expected values and using the fact that probability that x is bigger than or equal to expected value is always positive, and at the end also altering the structure a little bit to match it with what the structure that we're looking for. Okay. All right. Thank you and see you soon.